field, or let's say you're gathering data from a machine, you're gathering data from some kind of process, there will always be some amount of uncertainty built into any process. That's the beauty of statistics, right? There is always uncertainty. You can never have a deterministic outcome in the world of statistics. Right? So that is where this parameter epsilon comes into play. Essentially, that's basically the error term. So that's the error term that I associate with this equation. The combination of these basically is the definition of my linear regression equation. So if you look at it repetitively, we're going to be calling upon this equation. We'll be looking at the coefficients in detail. We're going to look at how this error actually influences how good my model is. That's what we are going to be looking at during this session as we go through. Now let's look at what some of the important points we basically have to consider when we work with regression equation. I mentioned about the fact that x1 and x2 has some kind of an influence on the y. Now, what are we doing here? We're basically testing some kind of a hypothesis. The hypothesis is, hey, x1 and x2 has an influence on y. They are not zero. Essentially, that's what we are testing. So that's basically the fundamental hypothesis. And it can extend to any number of x's. It can go up to x1 to x3. So there are k x's that you're trying to see if they have an influence on the left-hand side. That's basically the hypothesis that you're testing. But what is the actual hypothesis term? We will look at that in the subsequent slides. Now that is one of the first and fundamental understanding that we need to have as we step into this. And I spoke about this, the process of multiple regression tests if x1 and x2 have an actual impact on y itself. And also, we also look at how much of an impact does x1 and x2 have on y. I spoke about the weights. Right? So it's essentially telling you, hey, x1 impacts my y by so much. Because x1 changed by so much, my y is likely to change by so much. Because x2 changed by so much, my y is going to change by so much. So essentially, that's what we are actually trying to determine using this equation. But it's not a simple problem, right? I mean, you're not adding 1 plus 1 to get 2 here. If things are that simple, you don't really need a session like this where we are looking at the details of what is linear regression, right? And that is where the whole inferential aspects come. How do you understand that whatever you built here, whatever you call as an equation here, is actually something that is consumed. So essentially, that is what we'll be diving into as we move forward. Prediction, I think that's the exciting part, right? When you throw a set of factors into an equation and it gives an outcome, you're excited to see, okay, how much is that? How much is the outcome because of these factors? That's the exciting part. That comes right at the end. It needs to pass all these steps. You need to make sure that, hey, you have an equation that you can actually utilize for prediction. That's when you get the green flag. Go ahead and use it for prediction. I will pause here just to see if there are any questions before proceeding on to the next slide. Any questions from anyone? Okay, I take that as a no. Thank you. Alright, let's move on to the next slide here, where let's look at the key considerations that you associate with regression itself. So, the word linear itself has something interesting to convey to us. There is a word called line in it, and there is also the word called near built in. So what does it mean? So we are trying to do something that is actually close to a line. You need to find something that's close to a line. Essentially, that's what we are trying to fit here. Right? But when will something lie close to a line? That's basically the discovery process. Right? And one of the first considerations we have for linear regression to work is that a linear relationship actually exists between the dependent and the independent. So I have some charts in the upcoming slides, but I can just talk to what we are expecting. Right? So let's say I have a factor x1 in my x-axis and a dependent variable y on the y-axis. My expectation is all these points need to lie somewhere, where I can put a line, draw a line right through it, and I get straight line around which these points are actually distributed. Essentially, that's what a linear relationship is. An ideal linear relationship is every dot falls on the line that you draw right. But that's not going to happen. But we need to find a line where it's as close as possible to all the dots in the custom. Right? So that's one of the fundamental expectations and fundamental needs when you're working with linear regression. Now let's look at the second point. This is a very, very important point, what we call as multicollinearity. And this is very, very important when it comes to the interpretation side of it, or the inferential side of it. Independent variables that you have as part of an equation, they should not be correlated with each other. Why is that? Basically, let's say I have a factor that can actually be determined by another factor. Do I really need two factors there? I mean, the other factor seems to be able to perfectly explain what's happening on the other variable. What it does is it kind of destabilizes the coefficient. It doesn't know, okay, what is this? I mean, I'm trying to see that, hey, these two look very similar to me, but they're appearing as two separate terms. What do I do with it? So the model ends up, when the model fit, ends up compensating for it. So the first time you fit the model, you'll get one result. The second time you fit one. So you need very, very unstable distinction. We'll go into slightly more details about how to detect multicollinearity and all that as we move through this session. But that's another important point. You shouldn't have independent variables which are correlated with each other. It doesn't serve the purpose. Now, the next key consideration is basically the variance of residuals is a constant, right? And the term that we associate with this is called as homoscedasticity. Homoscedasticity basically means there is something that looks very, very similar, right? Here we are talking about the variance and of the residues. What are residues? So when you use any regression equation, I mentioned about the error term right at the end of this thing. So essentially, you get a prediction, and there is actually a deviation between the prediction that you made and what is actually observed. So that is basically what we call as a residue. Residue is basically there is some gap. Right? There is some gap between what was predicted and what was actually observed. So essentially, that residual is a very, very important factor that will be called upon. This term residual will be called upon during this presentation repeatedly, and it's something that is very, very important. The variance of residuals has to be a constant. What does that mean? You're going to get a lot of residuals. For every row in your data, you're going to get a residue. Now, if they're going to vary really wildly, can you get a straight line? Can you get a straight line that covers all the points? That's going to be very, very difficult. I will show some examples of how your data, when it's heteroscedastic, which is basically the opposite of homoscedasticity. When your data appears that way, there are some interesting patterns that emerge, which actually will help you infer, okay, hey, I seem to be seeing some kind of variance instability here among my residuals, and I need to take some steps to mitigate it. Right? So essentially, that's what homoscedasticity is. Very, very important when you're fitting regression models. The next concept is basically residuals are independent and normally distributed. Right? So this is another very, very important point, right? The word independent and normally distributed, you need to kind of separate it and then bring them together. When we say independent, what we mean by that is we shouldn't have one residual determining what another residual is going to look like. Typically it comes up due to a concept called as autocorrelation. There is something called as autocorrelation, where there is some kind of a pattern, a time-based pattern within your data, and where basically the residuals are correlated with each other over a period of time. There are other such cases where residuals are not independent. We can talk about it in later slides. But that's another important factor to look into when you are talking about residuals. Normally distributed, I think that's the fundamental expectation when you're fitting linear regression. The concept of multiple linear regression itself comes from the Gaussian family, right? It's actually a Gaussian family of distributions that actually help you set up a linear regression model. One of the fundamental expectations in Gaussian family of distributions, whatever the variate is or the residual is, it has to be normally distributed. Normal curves, I think we all would be very, very familiar. It's basically, we're talking about the same normal curve. This is a very, very fundamental expectation when you're dealing with linear regression. You need to have residuals which are normally distributed. If your residuals are skewed, once again, there is a message in it. It's telling you that, hey, there is something abnormal or there is some kind of a pattern here which might be turning your regression equation. Typically what happens is your regression equation is always trying to compensate for all the points you have in your data. When they are not normally distributed, it tells you that your regression line itself is not optimal. It's trying to compensate for something else. There's some kind of a data point or a series of data points which are not following the normal pattern, and you need to remediate before you can start using your regression equation for interpretation and prediction. So these are 4 fundamental parameters that we need to take into account when you are working with linear regression equations. So if you actually fail in any of these tests, right, you have to actually, when you fit your model, as soon as you fit your model, or also there are some pre-processing steps where you actually check what your variables relationships are among each of them. If some of these tests fail, then it's going to be a little hard for you to interpret your regression equation, or rather linear regression equation. You may probably need a non-linear equation, or you may need a different kind of a modeling technique altogether, unless you can remedy these problems through some steps. We'll talk about those steps also. Right? So these are basically the key considerations when you're dealing with linear regression. If you look at the subsequent slides, we're going to be clicking on each of these phrases that you see here, and how to determine it, how to make sure that these rules are actually met. There are some interesting ways to interpret them, which we will be looking at in subsequent slides. But fundamentally, it's about interpreting these, making sure that these rules are largely met. Having coming from the industry, to be honest with you, there are times when these rules do get violated, probably more often than not, right? In which case, either you have to switch your model, like I said, you may have to switch to a different modeling technique, or you still accept it for what it is and you proceed. You take the results with a pinch of salt and you move on. Unfortunately, that's basically what happens in the industry today. We are all kind of tuned to that kind of world. But from a research standpoint, at least, most of the times I've seen people simulating data and observations which largely follow these kind of patterns. So I think it's a different world altogether. In reality, it's very difficult to meet all of these conditions, but in the simulated world, yes, you can, and you can. So with that, I will just pause here. I'll just see if there are any questions before I move. Any questions from anyone? Now, let's look at the next slide where we will look at, let's go into the key consideration. What can we learn upfront about the data itself? Let's say you have a data set where you have your task is basically to build a regression model. Let's look at each of these parameters. I spoke about linearity. Right? and I mentioned that I have some slides where I will talk about how to determine linearity. One of the simplest ways to basically look at linearity itself is to plot your y against your x. Here I have chosen a random x and y from some data frame, and if you look at it, this is almost a perfect straight line. There are some strays here and there, but largely it's a perfect straight line that you're actually getting. So here we are talking about a strong positive linear relationship between the predictor variable and the dependent variable. So essentially that's what you get from this particular chart that you notice. Now the second one, you can still put a line. You can actually go from the left hand side top to the right hand side bottom. You can draw a line, but you notice there is a little more spread here in terms of the data itself. Right? So here I think the relationship is a little moderate, but the relationship is negative. So if you were to fit an equation here, I want to just jump a few points here. If you were to fit an equation here, you are likely to see a negative coefficient for this x variable when you are trying to predict the y variable. So essentially what it's telling you is, if your x variable, which has a negative coefficient, increases by a certain point, a 1 unit increase, let's take it that way, 1 unit increase on the x, which has a negative relationship with the y, that means your y is going to drop by a certain weight. That weight is what you get from that beta value that's associated with that x. Right? So essentially that's what a negative linear relationship actually means. Again, negative is not bad, it's okay. Largely we do see factors which can have a negative influence on outcome. They are also important, they also have to be studied. So that's basically a moderate negative linear relationship. Here is a case where there's absolutely no relationship. You put a line, you can fit a line anywhere here, it is never going to fall in the middle of all the points. There's no way you're going to be able to fit a line that will be able to cover all these points. So this is something that you will actually encounter very common in real life data. You're going to have, let's say you fit a line here. What will happen is these points will be represented well by that line, but all these strays, it won't be able to capture it. So in such cases, there are a couple of ways. Either you need to look at other techniques, or you need to try some kind of data transformations to see if some kind of relationship can be learned. But transformations won't help in most cases, especially in a chart if it looks this way. So you need to automatically infer that, hey, linear regression is not the way to go. Now that is the null or no relationship side of the word. Then comes the strong non-linear. Now here if you look at it, I can fit one straight line here. Yeah, I get it. But you can see how far it's going to be from the other set of points. So I can't fit a line. Now let's say I shift it and I put a line here, then it's not going to cover these points. So this is a very strict case of non-linear relationship. Technically, there are ways to handle this. You can actually fit two regression lines and do some kind of a combination of these two lines using some rules and conditions for this area here where the two lines meet, and you can get a non-linear regression line, although probably the relationship for each of these specific areas might be linear. So that is the fourth kind of relationship that you might encounter. In these cases, again, you can't use a perfect linear regression model for your effort. Right? So these are some of the scenarios from a linearity standpoint. Now coming to the next point around multicollinearity. Now multicollinearity, let's take this example here. I think there is some kind of a relationship that this is a data set about determining how health conditions impact poverty. Right? So that's the data. Now I've brought the dependent variable also as a part of the model just to build this equation, the correlation matrix out. You can see it is kind of interesting here. Now let's say I use obesity and high blood pressure. Let's see the patients or the respondents have these conditions, these two conditions, and I want to know how much these two variables actually influence poverty. Now the problem is these two variables have a strong correlation. 0.6 is going to be a significant correlation. Now in such cases what will happen is the model will struggle to determine, hey, is obesity more important or is it high blood pressure? So there are ways to actually remedy these kind of problems, and you can do it upfront. You notice we have not even built the model yet. We're still talking, in the pre-processing steps that are involved when you are actually building the regression. Now the remedies here are essentially like there's one simple remedy. You drop one of these variables and you move on. That's one way. But which variable to drop is a question that will always come. Now let's say you're building this model for a doctor. The doctor might say, hey, for me obesity is a cause for high blood pressure. So I would rather keep obesity and drop high blood pressure. So that's something that you need to have that little bit of domain related conversation. Okay, where am I building this model? Now for that model, what should I build into my equation so that it's useful for whoever is going to use the end product. Right? So essentially, that's basically what we need to consider when we do this. This is actually a good data where you have just two variables which are correlated. But in reality, you're actually going to get data points across multiple variables where there's a strong correlation between the variables themselves. Now, in such cases, there are alternative remedies. Again, these are things you need to do upfront, where there is a concept called as principal component factor analysis, where it actually mathematically helps you combine. Let's say there are 8 variables which are correlated. This principal component factor analysis, what it does is it can actually combine these variables. Let's say there is one factor which is a combination of 5 variables and another factor which is a combination of 3 variables. You can now create some new variables. These are basically, you will derive weights for each and every variable and you will multiply them to create this new variable which is representing 5 of the old variables, and another new variable which kind of represents the 3 variables which are correlated. Now you can now feed that into your equation and you can proceed down the path of linear regression. That's a slight deviation from this topic, but I thought it was important to mention that if you have multicollinearity in the data, all is not lost. There are remedies by which you can actually take care of it and you can proceed further. Right? But that's not the be all and end all of all remedies. I mean, there are other ways to also handle multicollinearity, but I will just stop with those two to highlight right now. And these are steps you can take upfront, even before going into building your regression. That's the very important part that you need to take. So I'll just pause here just to see if there are any questions before I proceed. Any questions from insofar I haven't had any question. I'm assuming everybody is either familiar with the topic already or it's I'm not clear.
Yes, Professor, go ahead.
Yeah, okay. Alright. The next is, let's go into the equation. So we've understood a few things about the data, we know what sort of variables are out there, we've selected some variables to be a part of the equation. Let's work with an example going forward. I mean, this would be simpler for all of us to pick up on forward, right? Now, here is a chemical process where there's some factory where they're creating some new chemicals, and one of the variables that they want to understand and what influences that variable is basically this variable called as impurity. I think impurity is probably this chemical has some kind of impurities within that, and they want to know the concentration of the impurity. What are all the at which the chemical reaction is actually happening. There is a catalyst which actually facilitates the chemical reaction. What is the concentration of the catalyst? And then the time, how long are we actually doing the reaction? So these are the 3 parameters that basically are being used to predict or infer about impurity. Right? Now let's go into the equation. Right? I mean, this equation has already been built, and if you look at it, impurity we are getting an intercept of minus 16.63, and these are the various other parameters. So for temperature, we are getting a coefficient of 0.79,